Hi everyone, my name is Andrey. At our company Digital Security, we carry out various research projects, and not so long ago, our attention was drawn by TrustZone technology, and we started our meticulous examinations of its security. We had Samsung Galaxy S8 mobile phone and started to explore its TrustZone implementation. After some initial research, we decided to concentrate on trusted applications executed there. And after all, we applied an interesting approach to fuzz them, and I'll tell you about it, and I'll tell you about the results we got. After that, we will review the exploitation of one of arbitrary code execution vulnerabilities we discovered. And to start with, we need to understand what ARM TrustZone technology is used for. As you know, the purpose of this technology is to isolate processing of sensitive data and other operations. It splits execution into two domains, secure world and normal world, and passes the execution of sensitive operations to the secure world. Well, inside the secure world, so-called trusted execution environment, or T, works. The T works in accordance with the standards developed by the Global Platform Association. In Samsung mobile devices, it is used for such cases as secure storage, access, authentication, biometrics, cryptographic operations, digital rights management. There are also such tasks as protecting secure world, protecting normal world from the secure one, and trusted user interface. So let's look at the implementation of this in Samsung mobile devices. Samsung, on its Exynos SoC devices, from Samsung Galaxy S3 to Samsung Galaxy S9, uses Trustonic implementation of trusted execution environment, secure OS named Kinibi. Formerly, it had been developed by Giesecke and Devrient company and had other names, Mobicore, this and T-Base. And later, the ownership changed. Kinibi implementation is closed source, but Trustonic published its reference sources for its normal world components at GitHub. And while all secure world SDK and documentation are under NDA, once there was a leak of Qualcomm sources to internet, and among that files, there were surprisingly Mobicore SDK as well. Although all this is not up to date and rather old, nevertheless, now we researchers community have documentation, useful headers, and static libraries. In the documentation, we can see the architecture of all system backed with the Kinibi operating system in secure world. Besides all parts in secure world, there are several components in normal world necessary to enable a system to use TrustZone. The scheme on the right presents a developer's view on such a system. And here we see that there are two API sets, Global Platform API and some legacy API, which is red. But while the Global Platform API is indeed implemented in the Kinibi, in Samsung it's not used, and all that is used is so-called legacy API. Let's start with normal world. In the case with Samsung Galaxy S8, it is where Android works. On the surface, there are client applications. They need to perform sensitive operations for which they utilize TrustZone. There are such services as KeyMaster that implements Android key store interface backed with TrustZone, Fingerprint for biometric services, Samsung Pay to make secure payments, and others. On the next level, in KNIB architecture, so-called trusted application connectors operate. They provide higher-level interfaces for client applications to work with secure world functions. There is a native interface in a set of libraries, and to some trusted services, there is also binder interface in TLC server application, TUI service applications as well. And for the purposes of administration of trusted applications, there is a root provisioning agent as an APK as well. Its task is to manage containers of trusted applications in secure world. These connectors, in their turn, use KNIB client API. It is implemented in two libraries, libmc client and libmc registry. libmc client contains the client API, global platform one and legacy one, to let client applications communicate with trusted ones, and libmc registry is dedicated to managing tasks such as, for example, installation of a service provider in KNIB space. All communications with secure world goes through a daemon. MC driver daemon is listening to a socket and dispatches commands which falls to an appropriate driver. It starts at system boot via emitter-C script. Like all sensitive components in Android, it is secured with SE Linux, and according to its policy, only MC driver daemon and some few applications can call trustonic kernel drivers. To enable communications from normal world to secure world, there must be a support in the Android kernel as well. Samsung, like other Android consumers, releases their kernels with sources. And there are also a number of community kernels that are being supported by community and customized by it. And usually it is easier to build a community kernel than the original one. In our research, we used bedstock kernel. When building a kernel, we can see TrustZone components in kernel config. In device drivers, we see Trustonic T driver, and this is the main bridge between normal world and secure world. To communicate with the user space, the driver creates 3 device nodes in dev file system as I/O control endpoints. One for T administration tasks, one for trusted user interface, and the third for communication between client applications and trusted applications. All these device nodes are also protected by SE Linux, so it's strictly controlled what knocks to TrustZone. And now the normal world implementation is clear, and let's dig to secure world. Almost all secure world components reside in one binary image in firmware archive as boot bin. In firmware archive, it can be found in the bootloader tar file. It has some custom format, and at first there is no information of its structure and contents. Great work on reversing this file was made by this Quarks Lab guy. He studied S-boot in Galaxy S6, but its general structure is the same for all junior models. And recently another work was published where a researcher managed to emulate S-boot image with Camo emulator. Great, but when we were researching, there was no such a good paper, so we could rely only the first one. S-boot conforms to the ARM trusted firmware design. It is a standard from ARM, which describes a reference bootloader implementation. Now it is renamed to Trusted Firmware A and Trusted Firmware M for application and mobile CPU profiles, respectively. The general structure of S-boot is as following. It consists of 4 big parts in accordance to ARM trusted firmware specification. Secondary bootloader, EL3 monitor, secure EL1 payload, and a non-secure payload, which is U-boot in our case. As for EL3 monitor, it's encrypted, so there is also an unpacker code for it. After some now about the secure EL1 payload part, which is in our case is T image exactly. After some reverse engineering and identifying the base address of the image, we see its components. Luckily, we didn't have to guess their names because there is a part named image header, which contains all the meta information on this image and as well names of all other parts. And having a sneaky peek at the leaked documentation of Qualcomm, we figure out the designation of all these parts. Here we have Kinibi microkernel, runtime manager, trusted drivers, internal API library mclib, and some trusted applications, all in one binary image. Now with those trusted applications or trustlets, although they are all similar, they differentiate in their functions to content management trustlets, service provider ones, and usual trustlets. Some of them are in a boot image, but most of them reside in Android file system. They are identified by GUID, and all trustlet files we found are also named as GUID plus TLBin extension. To exchange data between worlds, Kinibi utilizes shared memory buffers. They are called World Shared Memory or WSM buffers. These memory regions are mapped both in normal world and secure world, but on both sides they have different mappings, so they have different virtual addresses. And each world shared memory buffer is private for its trustlet. In communications between client application and trusted application, such buffers are called TCI buffers for Trusted Application Communication Interface. So the overall communication flow is as follows. First, user process opens a session with a trustlet. It sends such a request with the trustlet GUID to the daemon via the Unix socket. The daemon finds the trustlet file on the storage. Then it triggers Mobicore user driver IO control to ask Kinibi runtime manager to load it at the secure world side. When the driver receives such a request, it triggers an SMC instruction. And after that, this call is processed first at EL3 monitor, then it gets to Kinibi microkernel, and then the runtime manager dispatches it and loads the trustlet. Similarly, an allocation of TCI buffer works, and after that, both sides start dispatching loops where requests and responses are processed. That's it. As we know, trustlets communicate with client applications in Android user space and can be called from it directly. So we believe they are worth giving a more thorough look at them. Trustlet files have the MCLF format. The description of the format is publicly opened and can be found in Trustonic sources at GitHub. It contains a header, code section, initialized data section, and also an initialized space where stack also resides. And in the end of each trustlet file, there is the signature of the file. The executable code inside is 32-bit, like all T is. The header also contains some uninitialized fields, for example, a pointer to TCI buffer, its length, and a pointer to the MCLib entry point. This is the address of the code dispatching all internal API calls. It means that all calls to some external code are routed through one address in the trustlet header. So the code inside the trustlet is very isolated, and it means that we can easily emulate such code, and what is more exciting, we can easily fuzz it. And we can do it smartly. Of course, we can already, without additional preparations, can conduct some sort of a dump fuzzing. Just simply shoot data to trustlets via the TCI interface. Then we have trustlets in T environment, uncontrolled by us. We don't have any coverage information. We can get a signal about a crash only from kernel log, and after that we can study it with only static analysis. But we want to fuzz it another way, with all control and coverage guidance, to have all crash information and to explore crashes with all favorite tools. And we can do such a fuzzing with AFL. AFL has several modes to fuzz different targets. In our case, we have no sources, obviously, to recompile our target with AFL instrumentation. AFL Unicorn is a great tool, but it's not very convenient to debug code under Unicorn. Another way is to use Camo mode. It fuzzes executables of different architectures. In our case, we don't have a conventional executable file, of course, but Camo mode is very attractive. So to conduct smart fuzzing, we have to make some preparations. We must convert our MCLF trustlet to an ELF executable and somehow forward standard input to the trustlet code as a TCI buffer. It actually means that we are going to port the trustlet to the conventional Linux environment. When we elaborate on this challenge, we can meet the following problems. As I've already said, we should have some stub code to forward input. We should pack the stub with the trustlet image into one executable ELF. The trustlet code is not position independent, so it must be relocated in memory properly. We have to somehow pass execution to its code. We have to implement our version of internal library MCLib to work on Linux, and we must do it with all the trustlets we have, and so we must automate it for all trustlets. Let's have a look at each task. Our initial step will be the entry point for the resulting elf. It forwards standard input and pass it to a trustlet's entry point. So it's very simple code that occupies only several lines in C. To pass execution to a trustlet's entry point, let's assume we have its address as a symbol somewhere. So we are to call it as we call a function by its address in C. Then we must pack stub code and trustlet image into one executable. We do it in several steps. Firstly, compile stub code without linking. Then adding trustlet's entry point symbol to the resulting object file. Then we insert trustlet sections in proper addresses, and finally linking the object file to an elf executable. That's it. Now we have a working elf with trustlet's code in it, but any external call will cause a crash. To overcome this problem, we have to implement MCLeap API functions. Once again, we can have a look at the leaked Trustonic SDK to find out a list of all functions MCLeap has. Of course, there are many specific functions that would be hard to reproduce on our own due to much reverse engineering efforts and due to alien environment. But there are also some conventional functions like malloc and printf, which can be easily reproduced. Also, as you remember, all API calls are firstly dispatched in MCLeap entry point, so we also have to implement this function. And at last, it would be cool if we could automate these tasks for any trustlet. The task of importing trustlets is parameterized with the following data. Trustlet entry point, it's different in different trustlets, its sections locations, and the TCI buffer length. We decided to assign these parameters as variables in old good make files. And how can we get all these values from trustlet files? If you're used to IDA Pro, there are the IDA script tool and IDA batch mode for automatization, and some scripts to extract necessary values from the IDA database and these useful features. And our task is done. With the fashionable Ghidra, it's even more convenient with Ghidra headless mode. Now our trustlets are completely ported to the Linux environment. We can launch it and debug it, and we can start to fuzz it. There we can meet some problems. Not every toolchain for ARM turned out to suit for Camo, and not every binary will be instrumented by AFL write. But these problems are easy to overcome, and finally we succeed. Fuzzing works and starts to rain crashes. When we fuzzed all the 23 trustlets we had, we got out with 477 crashing test cases. Then we filtered out similar cases with AFL CMIN and had 225 cases. It's still too many, so we had to somehow automate crash analysis. To explore crashes, we decide to launch our binaries with test cases on a native ARM system and use its native tools. GDB for manual analysis, instrumentation tools like DynamoRio and Valgrind, because they are the only tools working with ARM code, and symbolic execution engines like the one in Anger framework. When testing them, we stumbled upon many hardships. Some GDB scripts like GDB Crash Analyzer outputs very poor and unreliable information. DynamoRio is a great DBI framework, but it refused to launch our binary with such a strange image layout. Valgrind has some useful tools, callgrind and memcheck, but the output is hard to use for automatic parsing. And Anger is Anger. It is known to be error-prone and slow, and to elaborate it to our problem needs much time. So GDB alone is our only friend. We developed a set of GDB scripts to help us identify the most interesting points and worked at our stub code and MCLib mocking code to log more information. Then we entered all gathered information in SQLite database. And this gave us a rather convenient way to explore crashes and filter out unpromising ones. Unpromising ones are, for example, that which results in call of some of unimplemented functions. MCLib has many functions we cannot reproduce. For example, a function to work with the SPI interface, a function to call driver interface, driver functions, support functions for such entities in Kinibi like secure objects. To elaborate on all these functions took a lot of reverse engineering and time. Doesn't worth the efforts. However, you can increase the accuracy of fuzzing results if you implement them. We decided to simply exclude such cases from our consideration. To filter out such cases, we can use simple SQL queries. For example, with this simple SQL query, we can get rid of cases resulting in the use of the SPI interface. This can significantly shrink the volume of interesting results. And after all, we found several real bugs. At least 2 of them are patched now. Let's consider the most interesting case. It's arbitrary code execution caused by heap overflow in the keymaster trustlet. The vulnerability is in the code parsing their encoded ASN1 structure in the TCA buffer. 2 fields in this buffer are used as sizes, one for locating memory and the other for copying that size of memory. When the second size is bigger than the first, non-surprisingly, heap overflow occurs. Such kind of bugs are known to lead to code execution on a system, so of course we try to make a full-fledged exploit from it. But first, let's consider what constraints for exploitation we have. Trusted applications in Kinibi are executed in their private virtual address space, so they are unable to access kernel or physical memory. The trustlet image and memory are divided into regions with different memory attributes. And as we checked, the TCA buffers reside in non-executable memory. These are these are all bad news, as they harden any memory corruption exploitation. The good news is that there is no ASLR in KNIB. It simplifies our exploitation, but however, they are going to implement it in new releases. With such mitigations, we can visualize a strategy like this. Firstly, we must find the function pointer in a writable location, like BSS section. Then relocate a heap chunk there via exploitation of the set heap overflow. Trigger allocation and copying this chunk to override the pointer. And finally, we must call the overwritten pointer to pass execution to a controlled location. Of course, to do it, we must know how the heap in KNIB works. We had to do some reverse engineering to find it out, but now there is no such need, because Lois and Felix in April at his talk at ZeroCon reviewed the heap in details, and you can see his slides to learn all about the KNIB heap. The interesting point here is how to relocate the heap to BSS section. In the logic of the allocator, the next address suitable for an allocation must meet some requirements. To find such an address, we used brute force. Our idea was based on the following. When the allocator traverses chunks to find a right place for a new allocation, it uses the next field. So if this field points to the chunk inside which it resides, the allocator will loop infinitely. We can use this fact to find out if our address in BSS section is suited for an allocation. That is enough to overwrite a function pointer in the BSS section and pass the execution to an arbitrary address. For a demonstration, we decided to pass it to the trustlet's entry point. Now there is a demo. Oh, yes, we are connecting to the phone. Then we launch brute force. It finds some suitable addresses, and then we launch our exploit with some kernel output. And in the end, it passes execution to the entry point of trustlets. This and this are similar. So now we can do a call at any address in the trustlets executable section. But we want more. We want to execute our own code. But all the places we can locate our shell code are non-executable. So the only possibility for us is to utilize some code reuse techniques. We also must remember that although we can rewrite stack since it resides in BSS section, there are canaries. It hinders ROP usage. Besides ROP, there is another option. We can always use job. Job stands for jump-oriented programming. It differs from ROP in that fact that while ROP uses return addresses to pass execution, with job, the destination address is taken not from stack, but from a register or an address in memory. To find such gadgets, we can use a great tool, ROP gadget. It will find all possible gadgets, and to get only job gadgets, we'll utilize a regular expression like this. Luckily, in our case, there are a lot of gadgets suitable for job. But discovering gadgets, it's still not it. We also need to build them into a chain. In ROP programming, the stack is used to place both gadget addresses and some parameters for them. In job, we need some place to locate them as well. And besides our simple gadgets, we need some sort of a super gadget that will advance execution with parameters by the chain. In the ARM instruction set, there is an instruction suitable for this purpose. Load memory increment address. As arguments, it takes a register. Let's call it pointer with a memory address and a set of registers to be filled. Then it fills those registers with the values from the memory the pointer points to, and then it increases the value of the pointer register by the size of the initialized registers it filled. So now, with the same set of gadgets, let's select only those containing LDMIA instruction. Somehow, Capstone, which ROP gadget uses, interprets it as LDMLO instruction. And we're happy there are such gadgets. So we just need to select one that suits our task and build our job shellcode. As a shellcode payload, let's, for example, print something from secure world to Android kernel log. So we are in the phone, and now we launch our exploit with kernel output in the same console. After all, it prints hello world. Sorry, maybe it's not very bright. Our exploit works. Printing hello world is, of course, good, but key master, where the vulnerability resides, is definitely much more interesting target. As it can access all key information, we can try to extract it. And in this blog post, a researcher extracted key master keys from TrustZone to break full disk encryption in Android. Although it was done with Qualcomm's trusted execution environment, I think details are not differ much, and you can try it also with Samsung. As another variant of post-exploitation steps, you can infiltrate further through trusted drivers and T-kernel, get to yield3 monitor, and from there do anything you want. So making out some takeaways. Porting a binary to a conventional environment turned out to be a rather easy task, and it is a portable approach, which means it can be done with any rather isolated code. Then such an executable can be fast with AFL, a very effective approach to find bugs. And exploiting founded bugs on a real system seem to be promising as well, as there is no ASLR in Kinibi and maybe other TrustZone implementation. No ASLR and other hardenings common for normal modern applications do it a very attractive target, as it is a starting point for infiltrate to TrustZone. And when the exploitation of the Android kernel starts to be a very hard problem, hitting it from TrustZone side seems to be an easier way than to do it from the Android user space itself. Yes, these some useful links on breaking TrustZone topic. And thank you for your attention.
Thank you very much, Andrey. Do we have any questions from the floor for Nico? No? Okay. Can we put these Slido questions up? I think we have a couple of questions there.
Resources. First of all, I recommend you practice and practice. So the less reading, more practice. Use some reliable instruments like AFL, like maybe Scapy for network fuzzing, and practice. Most crashing test cases were unexploitable because of our unimplemented functionality of many functions in MCLib. Maybe if we could implement most of them, I think we could get more real crashes. And it's not two real bugs, just two patched bugs. Rob gadgets were necessary for us in one of the scenarios of their exploitation, because we could override stack. So if there were no canaries, I think we could do this. But we decided to use job, and it turned out to be an easier way than use ROP.
Great. Unfortunately, there were no votes on any of those, so if there's any one other question on the floor, this is the last chance. If there's anyone out there who hasn't picked up one of the prizes yet. Got any questions? No? Okay, just give another thank you to Andrey.
Thank you very much.